This is the skull of a Pachycephalosaur, a 16-foot-long plant eater. Despite years of research, we're still trying to understand why it had this bizarre-shaped head.
The age of dinosaurs did not begin with dominance. It began in silence, in collapse, in a world that had nearly erased itself. Approximately 252 million years ago, life on Earth endured the most catastrophic biological crisis in its entire history. The event, now identified by geologists and paleontologists as the Permian-Triassic mass extinction, eliminated the overwhelming majority of complex organisms on the planet. Marine ecosystems were devastated first. An estimated 90% of oceanic species vanished. Coral reefs disappeared. Trilobites, which had survived for hundreds of millions of years, were permanently erased. On land, nearly 70% of vertebrate species went extinct. Entire ecological networks unraveled. The cause of this extinction was not a single impact or a brief anomaly. It was prolonged planetary destabilization. Massive volcanic eruptions in what is now Siberia released extraordinary volumes of carbon dioxide, methane, and sulfur dioxide into the atmosphere. These eruptions, referred to today as the Siberian traps, continued for hundreds of thousands of years. Greenhouse gases accumulated, global temperatures rose dramatically, ocean chemistry shifted toward acidification. Oxygen levels in both the oceans and the atmosphere declined. The Earth became hostile to complex life. Vast regions of the oceans turned anoxic, meaning they lacked sufficient oxygen to support marine organisms. Hydrogen sulfide may have accumulated in certain waters, poisoning entire ecosystems. Terrestrial environments suffered from extreme heat, drought, and instability. Forests collapsed. Soils eroded. Food webs disintegrated. This was not a temporary disturbance. It was a biological reset. In the aftermath, the planet was almost unrecognizable. Biodiversity was drastically reduced. Ecosystems were simplified. Ecological niches stood vacant across continents. The dominant species of the Permian world, including many synapsids and amphibians, were gone or severely diminished. But extinction, in evolutionary terms, creates opportunity. During the early Triassic period, life slowly began to reassemble itself. Recovery was not immediate. For millions of years, ecosystems remained fragile and unstable. Species diversity was low compared to pre-extinction levels. Extreme temperatures persisted. Atmospheric oxygen levels remained below modern concentrations. Yet within this unstable world, a group of reptiles known as archosaurs began to diversify. Archosaurs would eventually produce crocodilians, pterosaurs, dinosaurs, and birds. In the early Triassic, however, they were modest, relatively small creatures. They competed with surviving synapsids, including early relatives of mammals, and with various amphibian lineages that had endured the extinction. The defining anatomical characteristics of archosaurs were subtle but significant. They possessed openings in the skull in front of the eyes, known as antorbital fenestrae, which reduced weight. Their ankle structures allowed for more upright postures. Over time, certain archosaur lineages developed increasingly erect limb positions, positioning their legs directly beneath their bodies rather than sprawling outward. This anatomical shift was transformative. A sprawling posture, typical of many earlier reptiles, limits endurance and efficiency. Limbs positioned beneath the body improve locomotor efficiency, allowing for sustained movement and greater speed. In an unstable world where resources were scattered and predators were numerous, efficiency mattered. The Triassic world was dominated by a single massive landmass, Pangaea. This supercontinent stretched from pole to pole, encompassing nearly all terrestrial land. Its interior was vast, arid, and subject to extreme seasonal variation. Monsoonal systems developed along coastal margins, but central regions experienced severe drought. Deserts extended across enormous distances. Life in the Triassic required resilience. Among the archosaurs, evolutionary experimentation accelerated. Some lineages remained quadrupedal. Others became increasingly bipedal. Some specialized for carnivory, others for herbivory. Body sizes ranged from small, agile predators to medium-sized omnivores. Dinosaurs, when they first appeared around 230 million years ago in the late Triassic, were not giants. They were modest in size, lightly built, and relatively rare components of their ecosystems. Early dinosaurs such as Herrerasaurus and Eoraptor inhabited regions that are now part of South America. Fossil evidence suggests these animals were bipedal carnivores, equipped with sharp serrated teeth and grasping forelimbs. They likely hunted small vertebrates and insects. Their bodies were streamlined. Their tails were elongated for balance. Their hip structures displayed the defining features that would later characterize all dinosaurs. The hip anatomy of early dinosaurs represented a structural innovation. The acetabulum, the socket of the hip joint, was perforated. This open hip socket allowed the femur to articulate in a vertical orientation beneath the body. Combined with strengthened pelvic bones, this configuration supported an erect gait. It may appear subtle, but this anatomical refinement allowed for greater locomotor stamina. Over evolutionary time, this would prove decisive. Yet in the late Triassic, dinosaurs were not dominant. Other archosaurs, particularly crocodile-line relatives known as pseudosuchians, occupied apex predator roles. These animals were often larger and more heavily built than early dinosaurs. They filled ecological niches ranging from terrestrial hunters to semi-aquatic ambush predators. Dinosaurs coexisted with these formidable competitors for millions of years. During this period, the global climate continued to fluctuate. Volcanic activity associated with the gradual fragmentation of Pangaea intensified. Rift systems began forming as tectonic plates shifted. Magma intrusions released additional greenhouse gases. The Central Atlantic Magmatic Province, a massive volcanic province, erupted extensively near the end of the Triassic. These eruptions once again destabilized global ecosystems. Around 201 million years ago, at the boundary between the Triassic and Jurassic periods, another mass extinction occurred. Although less severe than the Permian catastrophe, this event significantly reduced biodiversity. Many large pseudosuchian archosaurs went extinct. Numerous amphibian and reptilian groups vanished. Dinosaurs survived. The reasons for their survival remain an active area of research. It is possible that their upright posture and efficient respiratory systems allowed them to cope better with fluctuating oxygen levels. Some evidence suggests that early dinosaurs may have possessed air sac systems similar to those found in modern birds, improving respiratory efficiency. Their growth rates may have been faster than many competitors. They may have been more adaptable in their diets and behaviors. Whatever the precise mechanisms, the outcome was clear. With many competitors eliminated, dinosaurs diversified rapidly during the early Jurassic. The breakup of Pangaea accelerated during this time. Continents began drifting apart, creating new coastlines and shallow inland seas. Climate patterns shifted toward warmer and more humid conditions in many regions. Vegetation flourished. Conifer forests expanded. Cycads and ginkgos became widespread. Ferns covered the forest understory. These expanding plant communities supported increasing populations of herbivores. Among Saurischian dinosaurs, one lineage began evolving into massive, long-necked herbivores known as sauropodomorphs. Early forms were relatively small and sometimes facultatively bipedal. But over time, natural selection favored increasing body size. Larger size provided digestive advantages. When processing fibrous plant material, it reduced vulnerability to predators. It allowed access to higher vegetation. Eventually, true sauropods emerged. Sauropods would become the largest terrestrial animals ever to walk the earth. Their bodies were supported by columnar limbs. Their necks extended to extraordinary lengths, in some species exceeding 10 meters. Their vertebrae contained air-filled cavities, reducing skeletal weight without compromising strength. Their tails were muscular counterbalances. The evolution of gigantism among sauropods was not accidental. It required coordinated changes in metabolism, skeletal architecture, and reproduction. Sauropods laid eggs rather than giving live birth, allowing them to produce numerous offspring without the constraints of gestation in large bodies. Their growth rates appear to have been rapid compared to modern reptiles. While sauropods expanded into herbivorous megafauna roles, theropod dinosaurs diversified as predators. Early Jurassic theropods were generally medium-sized, agile carnivores. They possessed serrated teeth designed for slicing flesh. Their hind limbs were elongated for speed. Their forelimbs varied in size and function depending on lineage. Some retained grasping ability, while others began reducing forelimb size relative to body mass. Predator-prey dynamics intensified. Ecosystems became increasingly structured around dinosaur interactions. Herbivorous populations grew in size and abundance. Predator lineages responded with increasing specialization. Some theropods developed stronger bite forces. Others evolved enhanced sensory capabilities. The Jurassic world was not static. It was dynamic, with evolutionary arms races shaping morphology over millions of years. Evidence from bone histology indicates that many dinosaurs grew rapidly during juvenile stages. Growth rings in fossilized bones suggest sustained metabolic activity. This has led to ongoing debate about dinosaur physiology. Were they cold-blooded like modern reptiles or warm-blooded like mammals and birds? Increasing evidence supports the interpretation that many dinosaurs possessed elevated metabolic rates compared to typical reptiles. Their upright posture, active lifestyles, and rapid growth patterns are consistent with a physiology that allowed sustained activity levels. This physiological flexibility would have been advantageous in fluctuating climates. Meanwhile, in the skies above Jurassic forests, pterosaurs dominated aerial ecosystems. Though not dinosaurs themselves, they were close relatives within Archosauria. Their membranous wings allowed powered flight long before birds appeared in the oceans. Marine reptiles such as ichthyosaurs and plesiosaurs occupied ecological roles analogous to modern dolphins and large marine predators. The Mesozoic era, encompassing the Triassic, Jurassic and Cretaceous periods, became the age of reptiles in a broad sense, but on land, dinosaurs were increasingly central. By the Middle Jurassic, dinosaurs were the primary large terrestrial vertebrates across most continents. Their fossil record appears in North America, South America, Africa, Europe, Asia, and even Antarctica. Continental drift continued separating landmasses, isolating populations, and encouraging diversification. Geographic isolation promotes speciation. As populations become separated by oceans or climatic barriers, they adapt independently. Over millions of years, distinct lineages emerge. This process generated extraordinary diversity within dinosaur clades. Some theropods evolved into large apex predators, such as Allosaurus, characterized by robust skulls and powerful jaws. Others remained small and agile. Among herbivores, Ornithischian dinosaurs diversified into multiple lineages, including early armored forms and beaked herbivores. The Ornithischians possessed a pelvic structure superficially similar to that of modern birds, though birds would later arise from theropod saurischians. This illustrates the complexity of evolutionary history, where similar anatomical configurations can evolve independently. Ornithischians developed specialized chewing mechanisms. Some evolved dental batteries composed of tightly packed teeth that continuously replaced themselves. This allowed efficient processing of tough vegetation. Complex jaw movements permitted grinding rather than simple slicing. Plant-dinosaur interactions intensified as vegetation evolved as well. During the late Jurassic and into the Cretaceous, flowering plants would eventually appear, altering ecosystems profoundly. But in the Jurassic, gymnosperms dominated. Conifers formed dense forests. Cycads and benititales thrived in warm climates. Ferns blanketed disturbed areas. Sauropods likely consumed large quantities of foliage daily, shaping forest structure. Their feeding heights created vertical stratification in plant communities. Smaller herbivores exploited lower vegetation. This partitioning reduced direct competition and allowed coexistence of multiple species within the same habitats. Predators targeted vulnerable individuals, juveniles, the sick, or isolated members of herds. Herding behavior may have evolved as a defensive strategy. Fossil trackways indicate that some dinosaurs moved in groups. Bone beds containing multiple individuals suggest social structures in certain species. The image of dinosaurs as solitary monsters is inconsistent with much paleontological evidence. Many species likely exhibited complex behaviors, including nesting colonies and parental care. Fossilized nests from later periods demonstrate that some theropods brooded their eggs. Skeletal arrangements suggest adults sitting atop clutches, wings spread. This behavior links them directly to modern birds. But in Chapter 1 of this long reign, the essential transformation was ecological consolidation. Dinosaurs transitioned from minor Triassic participants to dominant Jurassic architects of terrestrial ecosystems. Their success was not instantaneous. It was gradual, shaped by extinction events, climate shifts, continental drift, and anatomical innovation. They did not conquer a stable world. They inherited a wounded planet and adapted to its volatility. By the close of the Jurassic period, approximately 145 million years ago, dinosaurs had ruled terrestrial ecosystems for over 55 million years. This span alone exceeds the entire existence of humans by an almost incomprehensible margin. Yet their reign was only beginning. The Cretaceous period would bring further diversification, new plant communities, more complex food webs, and the emergence of some of the most iconic species ever discovered. But none of it would have occurred without the crucible of the Permian extinction, the harsh Triassic landscapes of Pangaea, and the evolutionary experimentation that followed. The age of dinosaurs was not inevitable, it was contingent. A sequence of catastrophes cleared ecological space. A lineage of upright archosaurs capitalized on opportunity. Anatomical refinements in hips, limbs, and respiratory systems enabled efficiency. Rapid growth and adaptive flexibility fostered diversification. For nearly 200 million years thereafter, dinosaurs would remain central to terrestrial life. Chapter 1 is not a story of giants. It is a story of survival. It is the account of how a devastated planet gave rise to a lineage capable of reshaping ecosystems on a continental scale. In the silence after the Great Dying, when forests were gone and oceans suffocated, evolution began again. And in that fragile beginning, the first true dinosaurs took their steps across a world that was ready once more to be ruled. The rise of dinosaurs was not dramatic. It was incremental, unfolding across millions of years through ecological shifts, anatomical refinement, and evolutionary persistence. In the late Triassic world, dinosaurs were still minor components of terrestrial ecosystems, yet the conditions shaping that world were steadily aligning in their favor. Approximately 230 million years ago, during the late Triassic period, the earliest true dinosaurs appeared in what is now South America. Fossil assemblages from Argentina and Brazil preserve some of the most important early representatives of this lineage. These animals were relatively small, lightly built, and predominantly bipedal. They did not tower above their environment. They moved quickly through it. One of the earliest known dinosaurs, Eoraptor, measured little more than 1 meter in length. Its skull was lightly constructed, equipped with sharp teeth suited for a carnivorous or possibly omnivorous diet. Its hind limbs were elongated, built for speed. Its forelimbs retained grasping capability. This was not yet a specialized apex predator. It was a generalist navigating a competitive ecosystem. Another early form, Herrerasaurus, was larger and more clearly carnivorous. It possessed serrated teeth designed for slicing flesh. Its pelvis and hind limb configuration already displayed key dinosaurian characteristics. The femur projected vertically beneath the body. The acetabulum was open. Musculature attachments indicate powerful hind limbs capable of sustained locomotion. These anatomical traits were subtle advantages. They did not guarantee dominance, but they improved efficiency. In evolutionary biology, marginal improvements compound over time. The late Triassic environment was still largely controlled by other archosaur groups, especially crocodile-line archosaurs known collectively as pseudosuchians. These reptiles occupied many ecological roles, including apex terrestrial predators. Some were large quadrupeds with armored bodies. Others were agile hunters. They were diverse and well established. Dinosaurs coexisted with them, often overshadowed in both size and abundance. The world they inhabited was unified under Pangaea. This immense supercontinent created climatic extremes. The interior experienced intense seasonal heat and drought. Coastal regions were somewhat more humid, influenced by monsoonal rainfall. River systems cut through arid landscapes, forming oases of biodiversity. These environmental gradients shaped evolutionary pathways. In arid interiors, animals capable of efficient locomotion across long distances had advantages. In fluctuating climates, dietary flexibility increased survival probability. Dinosaurs, with their upright posture and possible early respiratory efficiency, were well positioned to exploit these conditions. Another significant development during the Triassic was the diversification of synapsids, the lineage that would eventually produce mammals. Early mammal relatives persisted alongside archosaurs. They were generally small, often nocturnal, and ecologically constrained. They did not challenge dinosaurs for dominance at this stage, but they formed part of the broader competitive landscape. The Triassic world was not static. Tectonic forces beneath Pangaea were generating stress fractures. Rift valleys formed as continental plates slowly began separating. Volcanic systems became increasingly active. These geological processes would culminate in one of the defining extinction events that altered evolutionary trajectories. Around 201 million years ago, at the end of the Triassic period, massive volcanic eruptions associated with the Central Atlantic Magmatic Province released extraordinary volumes of lava and greenhouse gases. This event coincided with significant climatic upheaval. Atmospheric carbon dioxide levels spiked. Global temperatures increased. Ocean chemistry destabilized. Many large archosaurs, particularly several Pseudosuchian lineages, went extinct. Dinosaurs survived this crisis. Their survival reshaped terrestrial ecosystems. With competitors diminished or eliminated, dinosaurs rapidly diversified during the early Jurassic period. Ecological niches that had previously been occupied by other reptilian groups were suddenly available. Dinosaurs expanded into these vacant roles. The Saurischian lineage diversified into two primary branches, theropods and sauropodomorphs. Theropods remained primarily carnivorous and bipedal. They ranged from small, agile predators to increasingly larger forms. Skeletal evidence indicates improvements in skull strength and jaw mechanics. Muscle attachment sites suggest enhanced bite capabilities. Sensory structures in the skull imply well-developed vision and possibly acute hearing. Sauropodomorphs followed a different trajectory. Early members of this lineage were moderate in size and may have been facultatively bipedal, capable of moving on 2 or 4 limbs. Over time, body size increased dramatically. Forelimbs lengthened. Necks extended. The shift toward obligate quadrupedalism allowed support of increasing mass. This trend toward gigantism did not occur instantaneously. It unfolded gradually across millions of years. Selective pressures favored larger body sizes for herbivorous dinosaurs. Large size conferred digestive efficiency when processing fibrous plant material. It reduced vulnerability to predation. It allowed exploitation of higher vegetation layers. By the early Jurassic, sauropodomorphs were becoming some of the largest terrestrial animals of their time. Ornithischian dinosaurs also began diversifying. Early Ornithischians were small, bipedal herbivores with beaked mouths adapted for cropping vegetation. Their pelvic structure differed from Saurischians, with the pubis oriented backward. This configuration likely supported expanded digestive organs for fermenting plant matter. Ornithischians would later evolve into diverse groups including stegosaurs, ankylosaurs, hadrosaurs, and ceratopsians. But in the early Jurassic, they were modest in size and ecological influence. The key transformation of this period was numerical and ecological expansion. Fossil assemblages from early Jurassic formations across North America, Europe, Africa, and Asia indicate increasing dinosaur abundance. Trackways reveal widespread distribution. Skeletal remains demonstrate growing diversity. Continental drift accelerated during the Jurassic. Panjia began fragmenting into Laurasia in the north and Gondwana in the south. Rift valleys widened into proto-oceans. New coastlines formed. Shallow seas penetrated continental interiors. These geological processes influenced climate. As land masses separated, ocean circulation patterns changed. Coastal regions became more humid. Interior deserts contracted in some areas. Vegetation expanded in response to warmer, wetter conditions. Conifer forests flourished. Cycads and ginkgos became prominent. Fern prairies developed in disturbed habitats. These plant communities supported expanding herbivore populations. Sauropods evolved remarkable skeletal adaptations to sustain their immense bodies. Their vertebrae contained pneumatic cavities connected to air sac systems. This reduced skeletal weight while maintaining structural integrity. Their necks, supported by elongated cervical vertebrae, allowed feeding across wide vertical ranges without requiring constant body movement. Biomechanical analysis suggests that some sauropods maintained relatively horizontal neck postures, sweeping broad feeding arcs. Others may have adopted more elevated neck positions depending on species and ecological context. Their respiratory systems likely resembled those of modern birds, incorporating air sacs that improved oxygen extraction efficiency. This system supports high metabolic demand and large body size. Theropods continued refining predatory adaptations. Limb proportions suggest enhanced running capabilities. Some species developed stronger forelimbs for grasping prey. Dentition varied, reflecting dietary specialization. Evidence from bone histology reveals rapid growth rates in many early Jurassic dinosaurs. Growth rings indicate sustained metabolic activity rather than slow reptilian patterns typical of modern ectotherms. This has fueled the long-standing debate regarding dinosaur thermoregulation. Increasingly, paleontological evidence supports the view that many dinosaurs possessed elevated metabolic rates, possibly intermediate between traditional reptiles and modern birds and mammals. This metabolic flexibility would have supported active predatory behavior and rapid juvenile growth. Ecosystems became more structured around dinosaur interactions. Herbivores formed the base of terrestrial food webs. Predators regulated herbivore populations. Scavengers likely exploited carcasses. Insect communities diversified alongside plant expansion. Small vertebrates, including early mammals and amphibians, occupied ecological niches beneath dinosaur dominance. Dinosaurs were not isolated megafauna. They were integrated components of complex ecosystems. Fossilized trackways from Jurassic strata provide insight into behavior. parallel track patterns suggest group movement in certain species. Nesting sites, discovered in later formations, imply reproductive strategies involving egg-laying in communal areas. Parental care, once considered unlikely among large reptiles, is now supported by fossil evidence from later theropods and ornithischians. Brooding postures preserved in fossils demonstrate adults positioned over nests, wings extended protectively. These behaviors indicate social complexity beyond simplistic portrayals of solitary giants. During the Middle Jurassic, large theropods such as Megalosaurus and later Allosaurus emerged as apex predators in many regions. They possessed robust skulls with blade-like teeth. Bite mechanics suggest powerful neck-driven slashing attacks rather than bone-crushing forces seen in later tyrannosaurs. Sauropods reached extraordinary sizes during the late Jurassic. Species such as Diplodocus and Brachiosaurus exemplified the peak of sauropod gigantism. Their mass may have exceeded 30 to 50 metric tons in some cases. Supporting such mass required skeletal innovations. Limb bones were thick and columnar. Joints were reinforced. The center of mass was balanced by elongated tails. Circulatory systems must have generated sufficient blood pressure to supply elevated heads, particularly in long-necked species. The Jurassic landscape was dominated by these colossal herbivores. Predators evolved accordingly. Hunting strategies likely involved targeting juveniles or vulnerable individuals. Cooperative hunting remains debated, but some evidence suggests potential pack behavior in certain theropods. Continental separation further promoted speciation. As Laurasia and Gondwana drifted apart, isolated populations adapted to local environments. Geographic barriers such as emerging oceans prevented gene flow. Over millions of years, distinct lineages evolved. In Africa and South America, certain sauropod and theropod lineages developed independently from their northern counterparts. In Asia, unique, feathered theropods began appearing by the late Jurassic. The origin of feathers predates powered flight. Fossil discoveries from China reveal filamentous integumentary structures in small theropods. These early feathers likely served functions in insulation, display, or species recognition rather than flight. The evolutionary pathway toward avian flight was gradual. Modifications in forelimb length, shoulder articulation, and sternum structure eventually facilitated gliding and powered flight. By the late Jurassic, Archaeopteryx appeared in what is now Germany. This animal combined reptilian and avian traits. It possessed teeth, clawed fingers, and a long bony tail, yet also exhibited asymmetrical flight feathers indicative of aerodynamic function. Archaeopteryx demonstrates that birds evolved within theropod dinosaurs. The Jurassic world thus witnessed not only gigantism, but also miniaturization and experimentation in aerial locomotion. Marine environments during this period were dominated by reptiles such as ichthyosaurs and plesiosaurs, while pterosaurs controlled the skies. Dinosaurs remained primarily terrestrial, though later lineages would explore semi-aquatic adaptations. By the end of the Jurassic period, approximately 145 million years ago, dinosaurs had achieved ecological dominance across all major continents. Their reign at this point had already lasted tens of millions of years. Yet, the Cretaceous period would bring even greater diversification. Flowering plants would emerge, transforming terrestrial ecosystems. herbivorous dinosaurs would develop increasingly sophisticated chewing mechanisms. Predators would evolve unprecedented bite forces. Continental fragmentation would produce isolated evolutionary theaters. Chapter 2 marks the decisive transition. Dinosaurs were no longer peripheral participants in archosaur-dominated ecosystems. They had become the primary architects of terrestrial life. Their rise was not explosive, it was methodical. Shaped by extinction events, geological upheaval, and anatomical innovation, dinosaurs capitalized on opportunity with remarkable evolutionary success. From small bipedal hunters navigating Triassic river valleys to Jurassic giants reshaping forests, their transformation redefined the biosphere. The stage was set for over 150 million additional years of dominance. The age of dinosaurs was fully underway. By the beginning of the Jurassic period, dinosaurs were no longer marginal survivors of extinction, they had become central actors in terrestrial ecosystems. Yet, their dominance was still evolving. The Jurassic did not simply preserve dinosaur lineages, it amplified them. It was during this period that dinosaurs transformed from adaptable survivors into ecological titans. Approximately 201 million years ago, following the end Triassic extinction, the world entered a new phase of environmental restructuring. The supercontinent Pangaea was fragmenting. Tectonic rifts widened into shallow seas. Volcanic systems reshaped landscapes. Coastlines lengthened. Continental interiors, once arid and extreme, began experiencing shifts in humidity as oceanic influence increased. Climate during much of the Jurassic was warm, with no permanent polar ice caps. Atmospheric carbon dioxide levels remained elevated compared to modern standards. Global temperatures supported widespread vegetation growth across latitudes. Forests expanded into regions that had previously been inhospitable deserts. These changes created new ecological opportunities. Plant communities diversified. Conifers dominated upland forests. Cycads and Bennettitalians thrived in warm climates. Ginkgos spread across river valleys. Ferns carpeted disturbed ground following floods and storms. Vast floodplains formed along expanding river systems. With expanding vegetation came expanding herbivore populations. Sauropodomorph dinosaurs, which had already begun increasing in size during the late Triassic, accelerated their evolutionary trajectory toward gigantism. Early forms such as Plateosaurus were large but not yet colossal by the early Jurassic. True sauropods emerged, displaying definitive quadrupedal posture and dramatic neck elongation. Sauropods represented a radical solution to herbivory. Their necks extended to extraordinary lengths, in some species exceeding 9 or 10 meters. This allowed them to access vegetation across vertical and horizontal gradients without expending significant energy repositioning their massive bodies. Their heads remained relatively small compared to body size, minimizing distal weight at the end of long necks. Their vertebrae were pneumatized, containing air-filled cavities connected to an extensive respiratory air sac system. This system likely functions similarly to that of modern birds, permitting unidirectional airflow through the lungs. Such efficiency would have supported high oxygen extraction rates necessary for sustaining enormous body mass. The evolution of gigantism required multiple coordinated adaptations. Limb bones thickened and became columnar, supporting weight vertically rather than through flexed joints. Joint surfaces expanded to distribute compressive forces. Tails elongated to counterbalance neck mass and maintain center of gravity. Biomechanical modeling suggests that sauropods possessed relatively small heads and simple teeth because they did not rely on extensive oral processing of food. Instead, they likely swallowed vegetation, largely unchewed, and relied on large gut fermentation chambers to extract nutrients. Their digestive efficiency was enhanced by sheer volume. Large body size confers advantages in thermoregulation as well. Massive animals lose heat more slowly due to low surface area to volume ratios. In warm Jurassic climates, this may have stabilized internal temperatures, enabling sustained activity levels, while sauropods dominated herbivorous megafauna niches. Theropods continued refining predatory specialization. Early Jurassic theropods, such as Dilophosaurus, displayed elongated skulls with serrated teeth suited for slicing flesh. Their hind limbs were powerful and elongated, indicating cursorial capacity. Their forelimbs, though smaller than hind limbs, retained functional grasping claws. As the Jurassic progressed, theropods diversified into various ecological roles. Some remained medium-sized pursuit predators. Others increased in mass and power. Allosaurus, one of the most well-known late Jurassic theropods, exemplifies this escalation. Measuring up to 8 to 10 meters in length, Allosaurus possessed a robust skull with blade-like teeth. Biomechanical studies indicate that its bite force may not have matched later tyrannosaurs in raw power, but its skull was adapted for delivering slashing bites driven by strong neck musculature. It may have attacked by inflicting repeated wounds rather than relying on bone-crushing force. Fossil assemblages from formations such as the Morrison Formation in North America reveal ecosystems structured around sauropod herbivores and large theropod predators. Bone beds containing multiple sauropod individuals suggest herd behavior, or at least group movement patterns. Predation pressure likely influenced social behavior. Juveniles may have been particularly vulnerable. Rapid growth rates, observed in sauropod bone histology, suggest evolutionary pressure to reach large size quickly, reducing susceptibility to predators. Ornithischian dinosaurs also expanded during the Jurassic. Stegosaurs emerged as distinctive herbivores, characterized by rows of dermal plates along their backs and spikes on their tails. The function of these plates has been debated extensively. Hypotheses include thermoregulation, species recognition, and display. Vascular impressions within fossilized plates suggest blood flow, supporting potential thermoregulatory or display functions. The tail spikes, often referred to as thagomisers, were clearly defensive structures. Evidence of healed bite marks on stegosaur plates indicates survival following predator attacks, implying that interactions between stegosaurs and large theropods were common. Another Ornithischian group, early ankylosaurs, began developing dermal armor embedded within their skin. Osteoderms formed protective shields across the back and flanks. This defensive strategy represented a different solution to predation pressure, passive protection rather than size or speed. The Jurassic was characterized by evolutionary experimentation in both offense and defense. Dinosaurs were not evolving in isolation. Other reptilian lineages occupied marine and aerial ecosystems. Pterosaurs, close relatives within Archosauria, achieved powered flight through membranous wings supported by elongated fourth fingers. They filled ecological niches ranging from small insectivores to large fish-eating predators. Marine reptiles such as ichthyosaurs resembled modern dolphins in body shape, adapted for streamlined swimming. Plesiosaurs exhibited long necks and flippered limbs suited for maneuvering in shallow seas. These groups illustrate that the Jurassic was a time of reptilian diversification across multiple environments. Yet on land, dinosaurs increasingly structured ecosystems. Continental drift played a significant role in shaping diversity patterns. As Laurasia and Gondwana separated, populations became geographically isolated. Isolation reduces gene flow and promotes divergent evolution. Regional faunas developed distinct characteristics. In Africa and South America, certain sauropod lineages diverged from those in North America and Europe. In Asia, theropod diversity expanded along independent trajectories. Climatic gradients across latitudes created additional environmental filters. Polar regions during the Jurassic were warmer than today, lacking permanent ice caps. Fossil evidence from Antarctica indicates the presence of dinosaur species adapted to high-latitude environments. Though seasonal darkness would have occurred, temperatures were milder than modern polar climates. This suggests physiological flexibility among dinosaurs. The ability to tolerate varying photoperiods and seasonal changes implies metabolic capabilities beyond those of modern ectothermic reptiles. Bone microstructure studies reveal fibrolamellar tissue in many dinosaur species, indicative of rapid growth and sustained metabolic activity. Such evidence supports the hypothesis that at least some dinosaurs maintained elevated internal body temperatures either through endothermy or mesothermy. The debate over dinosaur metabolism remains complex, but the Jurassic record increasingly supports active, dynamic organisms rather than sluggish reptiles. Another transformative development during the Jurassic was the continued evolution of feather-like integumentary structures among theropods. Fossil discoveries from China, particularly from the Tianyu and Liaoning regions in later deposits, reveal filamentous structures on small theropods. Although many of these fossils date to the early Cretaceous, the evolutionary origin of feathers likely began in the Jurassic. These protofeathers may have served insulation functions, enabling small theropods to maintain stable internal temperatures. They may also have been used for display, signaling, or species recognition. Miniaturization occurred in several theropod lineages. Some species evolved smaller body sizes, lighter skeletons, and elongated forelimbs. These trends would eventually culminate in the emergence of avian flight. Archaeopteryx, discovered in late Jurassic deposits of Germany, provides critical evidence for this transition. It possessed flight feathers with asymmetrical veins, indicating aerodynamic capability. Yet, it retained teeth, clawed fingers, and a long bony tail. Archaeopteryx was not the first dinosaur with feathers, nor was it fully equivalent to modern birds. It represents a transitional form within a continuum of theropod evolution. Flight likely evolved incrementally, beginning with gliding or wing-assisted incline-running behaviors before achieving full-powered flight. The Jurassic, therefore, witnessed both the evolution of the largest terrestrial animals in Earth's history and the emergence of one of the smallest and most transformative lineages, birds. Ecosystems during this period were complex and interconnected. Herbivorous dinosaurs influenced plant community structure through selective feeding. Large sauropods may have maintained open woodland environments by browsing on high vegetation. Stegosaurs and smaller Ornithischians exploited lower strata. This vertical stratification reduced direct competition and supported coexistence. Predators exerted top-down control on herbivore populations. Scavengers, including smaller theropods, likely consumed carcasses. Insect populations flourished within forest ecosystems. Early mammals, though small and often nocturnal, occupied insectivorous and omnivorous niches beneath dinosaur dominance. The Jurassic was not merely an age of giants. It was a period of ecological stabilization following the volatility of the Triassic. For approximately 56 million years, from 201 to 145 million years ago, dinosaurs consolidated control over terrestrial ecosystems. Their diversity increased steadily. Morphological innovation accelerated. Continental fragmentation produced regional variation. Yet, this stability did not imply stagnation. Evolution continued refining body plans. Sauropods experimented with neck lengths and body proportions. Theropods diversified skull shapes and limb ratios. Ornithischians developed increasingly elaborate defensive and feeding adaptations. Toward the end of the Jurassic, environmental changes began setting the stage for the Cretaceous period. Sea levels fluctuated. New inland seas formed. Floral communities gradually shifted. The dominance achieved during the Jurassic would serve as a foundation for further expansion. By 145 million years ago, dinosaurs had ruled terrestrial ecosystems for over 55 million years. In human terms, this duration is nearly beyond comprehension. The entire evolutionary history of the human genus spans less than 3 million years. The Jurassic dominance of dinosaurs alone was nearly 20 times longer. Yet their reign would continue for another 80 million years. Chapter 3 represents the consolidation of power. The Jurassic did not merely maintain dinosaur lineages, it elevated them into ecological architects. It produced the largest land animals ever known. It witnessed the early evolution of birds. It established predator-prey dynamics that would define the Mesozoic. Dinosaurs were no longer experimental archosaurs navigating a recovering world. They were the rulers of forests, floodplains, and continental interiors. The age of giants had begun. By the close of the Jurassic period, dinosaurs had already dominated terrestrial ecosystems for more than 50 million years. They were diverse, geographically widespread, and ecologically integrated. Yet, the transition into the Cretaceous period marked a new phase of evolutionary escalation. If the Jurassic established dinosaur supremacy, the Cretaceous refined it, intensified it, and pushed it toward both its greatest complexity and its eventual collapse. Approximately 145 million years ago, tectonic fragmentation of Pangaea had progressed significantly. Laurasia in the north and Gondwana in the south continued separating into recognizable continental masses. The early Atlantic Ocean widened. South America drifted away from Africa. India began its long migration northward. These movements reshaped ocean circulation patterns, altered climate regimes, and produced increasing geographic isolation among terrestrial populations. Isolation is a powerful evolutionary engine. When populations become separated by oceans, mountain ranges, or climatic barriers, gene flow ceases. Over millions of years, natural selection acts independently in each region. Small anatomical differences accumulate. Behaviors shift. Ecological specializations intensify. Eventually, entirely new lineages emerge. The Cretaceous period became a mosaic of regional dinosaur faunas. Global climate during much of the Cretaceous, remained warm. Atmospheric carbon dioxide levels were elevated. Polar regions were free of permanent ice sheets. Sea levels rose significantly, flooding continental interiors and creating shallow epicontinental seas. North America, for example, was divided by the Western Interior Seaway, separating eastern and western land masses for millions of years. These environmental changes fostered ecological complexity. One of the most transformative biological innovations of the Cretaceous was the rise of flowering plants, or angiosperms. Prior to their emergence, terrestrial plant communities were dominated by gymnosperms such as conifers and cycads, along with ferns and horsetails. Angiosperms introduced new reproductive strategies, including enclosed seeds and often animal-mediated pollination. Their rapid diversification altered terrestrial ecosystems profoundly. Flowering plants spread across floodplains and forest understories. They produced leaves with higher nutritional value and faster growth rates compared to many gymnosperms. This created new feeding opportunities for herbivorous dinosaurs. In response, herbivorous lineages evolved increasingly specialized dental and jaw adaptations. Ornithischian dinosaurs underwent remarkable diversification during the Cretaceous. Among them, hadrosaurs, often referred to as duck-billed dinosaurs, developed complex dental batteries composed of hundreds of tightly packed teeth. These teeth formed grinding surfaces capable of processing fibrous plant material efficiently. Replacement teeth continuously formed beneath active ones, ensuring functional chewing surfaces throughout life. Hadrosaurs were not solitary animals. Fossilized bone beds containing numerous individuals suggest herd behavior. Trackways indicate coordinated movement. Their cranial crests, hollow in many species, may have functioned in vocal communication, species recognition, or display. Another major Ornithischian radiation involved ceratopsians, the horned dinosaurs. Early forms were relatively small and bipedal. By the late Cretaceous, they evolved into large quadrupedal herbivores with elaborate cranial ornamentation. Triceratops, one of the most iconic late Cretaceous dinosaurs, possessed 3 facial horns and a broad bony frill extending from the back of its skull. These structures likely served multiple functions, including defense, species recognition, and sexual display. Bone pathologies in fossil specimens reveal evidence of horn-to-horn combat, suggesting intraspecific competition. Ankylosaurs continued refining their defensive strategy. Their bodies were encased in bony armor composed of osteoderms embedded within the skin. Some species developed massive tail clubs capable of delivering powerful blows. Biomechanical studies suggest these clubs could fracture bone, providing effective defense against large predators. While herbivores diversified and specialized, theropod predators escalated in size and power. The early Cretaceous witnessed the diversification of coelurosaurs, a theropod group that included both small feathered species and the ancestors of tyrannosaurs. Feathers, once simple filamentous structures, became more complex. Some species developed symmetrical veined feathers for insulation and display. Others evolved asymmetrical flight feathers, facilitating gliding and powered flight. Birds diversified during the Cretaceous, branching into multiple lineages. Some retained teeth and clawed wings. Others gradually lost these primitive features. Avian flight styles diversified, from soaring to flapping to perching behaviors. Yet, the Cretaceous also produced some of the most formidable non-avian theropods in history. In Gondwana, particularly in South America and Africa, large abelisaurids dominated apex predator niches. These theropods possessed short skulls, reduced forelimbs, and powerful hind limbs. Their cranial ornamentation suggests potential display functions. In Asia and North America, tyrannosauroids gradually increased in size. Early forms were relatively modest predators. Over millions of years, this lineage culminated in Tyrannosauroids rex. Tyrannosaurus rex, appearing in the late Cretaceous, approximately 68 to 66 million years ago, represented one of the most powerful terrestrial predators ever to exist. Its skull was massive, reinforced by fused nasal bones capable of withstanding extreme stress. Bite force estimates exceed 6,000 kilograms of pressure, sufficient to crush bone. Its teeth were thick and conical rather than blade-like, designed for puncturing and crushing rather than slicing. This suggests feeding behavior that included bone consumption, extracting maximum nutritional value from carcasses. Forward-facing eyes provided binocular vision, enhancing depth perception. Olfactory bulbs within the brain case indicate a highly developed sense of smell. Tyrannosaurus was not merely large, it was biomechanically optimized. While tyrannosaurs dominated Laurasian land masses, other theropods occupied specialized ecological niches. Dromaeosaurs, such as Velociraptor, were smaller but agile predators equipped with enlarged sickle-shaped claws on their hind feet. Their anatomy suggests active pursuit and possibly pack behavior, though evidence remains debated. One of the most unusual Cretaceous theropods was Spinosaurus. Unlike most theropods, Spinosaurus exhibited clear adaptations for semi-aquatic life. Its elongated crocodile-like snout contained conical teeth suited for grasping fish. Its bones were unusually dense, reducing buoyancy and aiding underwater submersion. Recent fossil discoveries indicate a paddle-shaped tail, further supporting aquatic propulsion. Spinosaurus illustrates that dinosaur evolution was not confined to terrestrial dominance. It explored ecological boundaries. Continental separation during the Cretaceous intensified regional differentiation. South America developed unique lineages, isolated from North America for millions of years. Africa harbored its own distinctive fauna. Asia became a center of feathered theropod diversification. Antarctica, though warmer than today, supported dinosaur communities adapted to seasonal darkness. Polar dinosaurs demonstrate physiological resilience. Bone histology suggests continued growth during winter months, implying metabolic regulation rather than seasonal dormancy. The Cretaceous world was complex and stratified. Ecosystems were structured vertically and horizontally. Forests contained multiple feeding layers. Large sauropods, though less dominant than in the Jurassic, persisted in certain regions, particularly in South America. Titanosaurs, a derived sauropod lineage, became widespread in Gondwana. Some titanosaurs reached enormous sizes, rivaling or exceeding Jurassic giants. Herbivore diversity reduced direct competition through niche partitioning. Hadrosaurs exploited certain plant communities. Ceratopsians focused on low-growing vegetation. Ankylosaurs utilized armored defense while feeding close to the ground. Predators responded to prey availability and specialization. Fossil evidence indicates complex trophic interactions. Bite marks on herbivore bones match theropod dentition. Coprolites containing bone fragments confirm bone consumption. Nesting sites reveal reproductive strategies, including colonial nesting and parental care. One of the most significant developments of the Cretaceous was the increasing sophistication of dinosaur reproductive behavior. Fossilized nests from Mongolia and North America show eggs arranged in circular patterns. Some theropod fossils preserve adults positioned over clutches, wings spread. This brooding posture parallels modern birds. Embryonic remains within eggs reveal rapid developmental growth. Bone microstructure suggests that hatchlings were relatively precocial, capable of movement shortly after birth in some species. Social behavior likely played a role in survival. Herd movement, vocal communication via resonant crests, and defensive group formations may have reduced predation risk. The Cretaceous period spanned approximately 79 million years, from 145 to 66 million years ago. During this time, dinosaurs maintained uninterrupted dominance over terrestrial ecosystems. Mammals persisted but remained small, generally nocturnal and ecologically constrained. Some developed specialized dentition and increased brain size, yet they did not challenge dinosaur supremacy. The global climate during the mid-Cretaceous reached one of the warmest intervals of the Mesozoic. Tropical conditions extended toward high latitudes. Shallow seas teemed with marine reptiles and ammonites. Pterosaurs continued flying overhead, though avian competition gradually increased. Then, approximately 66 million years ago, stability ended. An asteroid approximately 10 to 12 kilometers in diameter struck near present-day Chicxulub on the Yucatan Peninsula. The impact released energy equivalent to billions of nuclear weapons. Shockwaves circled the globe. Debris ejected into space re-entered the atmosphere, generating intense thermal radiation. Wildfires spread across continents. Dust and sulfate aerosols injected into the stratosphere blocked sunlight. Photosynthesis collapsed. Global temperatures plummeted in the aftermath, producing an impact winter. Food chains unraveled from the bottom upward. Large non-avian dinosaurs, dependent on stable plant communities and complex food webs, could not survive the rapid environmental collapse. Within a relatively short geological time frame, they vanished. Birds survived. Small body size, dietary flexibility, and perhaps sheltering behaviors may have contributed to their survival. Mammals also survived, poised to expand into newly vacant ecological niches. The Cretaceous period represents both the pinnacle and the termination of dinosaur dominance. For nearly 200 million years, from their modest origins in the Triassic through Jurassic gigantism and Cretaceous specialization, dinosaurs were the central architects of terrestrial ecosystems. Chapter 4 captures the height of their evolutionary sophistication. It was a world of armored herbivores, bone-crushing predators, feathered flyers, and semi-aquatic hunters. And continents drifted. Plants transformed landscapes. Ecosystems layered into intricate networks. And for tens of millions of years, stability prevailed, until a single astronomical event ended the reign of giants. Yet their story did not conclude with extinction. Birds carried their lineage forward. Fossils preserved their legacy. Modern ecosystems still reflect evolutionary pathways shaped under dinosaur rule. The Cretaceous was not simply the final chapter of dominance. It was the culmination of nearly 200 million years of evolutionary experimentation ecological integration, and planetary transformation under dinosaur supremacy. When the Cretaceous period reached its midpoint, the dinosaur empire was not weakening. It was at its most intricate, its most specialized, and in many regions, its most powerful. Ecosystems across the planet had been structured around dinosaur dominance for more than 100 million years. Predator and prey relationships were refined. Herbivore guilds were diversified. Continents were fragmented into evolutionary theaters that fostered unique lineages. The world was warm. Sea levels were high. Shallow inland seas divided continents into isolated landmasses. Atmospheric carbon dioxide concentrations were elevated compared to modern levels, maintaining greenhouse conditions. Polar regions supported forests rather than ice sheets. Seasonal darkness existed at high latitudes, but temperatures remained moderate. This was a planet fundamentally different from today. In North America, the western interior seaway split the continent into two landmasses, Laramidia in the west and Appalachia in the east. This geographic division persisted for millions of years, isolating populations and driving divergent evolutionary trajectories. On Laramidia, dinosaur diversity reached extraordinary levels during the late Cretaceous. Hadrosaurs flourished in multiple species, each distinguished by variations in cranial crest morphology, dentition, and body proportions. Lambeosaurines developed elaborate hollow crests extending from their skulls. The internal structure of these crests formed complex nasal passageways, suggesting roles in vocal resonance. Acoustic modeling indicates that these animals may have produced low-frequency calls capable of traveling long distances across floodplains. Such communication would have been advantageous in herd coordination. Bone beds containing hundreds of hadrosaur individuals indicate mass mortality events, possibly from flooding or drought. These assemblages provide strong evidence for gregarious behavior. Herding may have offered protection against predators and enhanced reproductive success. Ceratopsians also radiated dramatically across Laramidia. Triceratops became one of the dominant herbivores of the late Cretaceous North American plains. Its massive skull could exceed 2 meters in length. The frill, composed of parietal and squamosal bones, was not merely ornamental. It likely served as a muscle attachment site for powerful jaw musculature, as well as a defensive barrier. Microscopic analysis of Triceratops bone tissue reveals rapid growth rates during juvenile stages. Like many large dinosaurs, it appears to have reached adult size relatively quickly compared to modern reptiles. Pathological specimens show healed injuries on frills and horns, suggesting intraspecific combat. These confrontations may have been related to mating competition or territorial disputes. Ankylosaurs coexisted alongside ceratopsians and hadrosaurs, occupying low browsing niches. Their bodies were encased in heavy armor composed of bony plates embedded in the skin. Some species possessed tail clubs, formed from fused vertebrae and enlarged osteoderms.
Finite element analysis of ankylosaur tail clubs suggests they were capable of delivering high-impact forces. Bite marks and healed fractures on ankylosaur fossils indicate survival after predator encounters. While herbivores diversified defensively and socially, predators escalated in offensive capability. Tyrannosaurus rex emerged as the apex predator of late Cretaceous North America. Measuring up to 12 meters in length and weighing approximately 8 to 9 metric tons, it combined size, sensory acuity, and extraordinary bite force.
Its skull was structurally reinforced by fused nasal bones and thickened cortical bone. Teeth were large, banana-shaped and robust. Unlike earlier theropods that relied primarily on slicing, Tyrannosaurus could crush bone. Coprolites attributed to tyrannosaurids contain pulverized bone fragments, confirming osteophagy. Its forelimbs were reduced but muscular, equipped with 2 functional claws. While once dismissed as vestigial, biomechanical studies indicate these limbs retained strength and may have assisted in prey handling or rising from resting positions. Tyrannosaurus was not alone among apex predators. In South America, abelisaurids, such as Carnotaurus, dominated large predator niches. Carnotaurus possessed a short, deep skull with reduced forelimbs, even smaller proportionally than those of Tyrannosaurus. Its skull morphology suggests a powerful but differently structured bite mechanism. Cranial ornamentation, including horn-like structures above the eyes, may have served display or combat functions. South America also supported titanosaurs, enormous sauropods that persisted long after sauropods declined in Laurasian ecosystems. Titanosaurs such as Argentinosaurus may have exceeded 30 meters in length. Their wide distribution across Gondwana indicates ecological success in diverse habitats. Africa, during the mid to late Cretaceous, hosted unique assemblages as well. Spinosaurus, already adapted for semi-aquatic predation, inhabited river systems rich in fish. Fossil evidence suggests elongated neural spines forming a sail-like structure along its back. The function of this sail remains debated. Hypotheses include thermoregulation, display, or fat storage. Recent discoveries of dense limb bones and a paddle-shaped tail support the interpretation that Spinosaurus was at least partially aquatic, possibly pursuing prey underwater. This ecological specialization demonstrates the breadth of dinosaur adaptive potential. Asia became a center of feathered theropod diversity. Fossil beds in China preserve exceptional specimens with preserved integumentary structures. Dromaeosaurs, oviraptorosaurs, and troodontids exhibited varying degrees of feather complexity. Some species show evidence of wing-assisted locomotion. Others display elaborate plumage likely used for display. Oviraptorosaurs provide insight into reproductive behavior. Multiple fossil specimens preserve adults in brooding posture over nests of eggs. These animals position their forelimbs around clutches in a manner strikingly similar to modern birds. Such evidence reinforces the evolutionary continuity between non-avian theropods and birds. Avian lineages diversified significantly during the Cretaceous. Early birds such as enantiornithines occupied arboreal niches, others developed aquatic adaptations. While many retained teeth, gradual reduction and eventual loss of teeth occurred in certain lineages. Flight styles diversified, from flapping to soaring to perching behaviors. Pterosaurs continued occupying aerial niches, though by the late Cretaceous, many smaller pterosaur species declined, possibly due to competition with birds. Large Ajdarchid pterosaurs, with wingspans exceeding 10 meters, dominated certain regions. These animals likely stalked terrestrial prey in addition to flying. Marine ecosystems were equally dynamic. Mosasaurs, large marine reptiles, became apex predators in Cretaceous seas. Plesiosaurs persisted, while ammonites flourished as important components of marine food webs. Terrestrial ecosystems, however, remain centered on dinosaur interactions. Fossilized trackways reveal complex movement patterns across floodplains. Nesting colonies indicate reproductive site fidelity. Isotopic analysis of fossil bones suggests migratory behavior in some species, possibly tracking seasonal vegetation changes. Climatic conditions during the mid-Cretaceous were among the warmest of the Mesozoic. Oceanic anoxic events occurred intermittently, reducing marine oxygen levels and altering global carbon cycles. Yet, terrestrial ecosystems remained relatively stable for millions of years. This stability fostered increasing specialization. Herbivores refined feeding strategies. Predators optimized hunting tactics. Social behaviors likely grew more complex.
Braincase studies in certain theropods reveal relatively large brain-to-body ratios compared to other dinosaurs, suggesting advanced sensory processing and coordination.
Troodontids, for example, possessed large orbits and expanded cerebral hemispheres. Their intelligence relative to body size approached that of modern birds. This was not a world of simple reptiles driven solely by instinct. It was a biosphere shaped by millions of years of evolutionary feedback. By approximately 70 million years ago, dinosaurs had dominated terrestrial life for nearly 160 million years. No other large vertebrate group in Earth's history has maintained such prolonged supremacy. Yet, beneath this apparent stability, tectonic and astronomical forces continued operating. India drifted northward toward Asia. Volcanic provinces remained intermittently active. Asteroid impacts, though generally minor, continued as part of Earth's cosmic environment. Around 66 million years ago, one such asteroid altered the trajectory of life permanently. The Chicxulub impactor struck the Yucatan Peninsula with unimaginable force. Seismic waves radiated outward. Ejecta blanketed the globe. Atmospheric particulates blocked sunlight. Photosynthesis halted. Primary producers collapsed. Herbivores starved. Predators followed. Non-avian dinosaurs, despite their long dominance, could not withstand the rapid environmental collapse. Their extinction was geologically abrupt. Birds survived, likely due to small body size, dietary flexibility, and possibly sheltering behaviors. Mammals survived as well, poised to diversify into vacant niches. Chapter 5 represents the apex of dinosaur specialization and ecological integration. It was a world of herding hadrosaurs resonating across floodplains, horned ceratopsians engaging in combat, armored ankylosaurs defending against bone-crushing predators, and tyrannosaurs dominating apex roles. It was a world where feathered theropods brooded nests and semi-aquatic hunters navigated rivers. For nearly 200 million years, dinosaurs shaped terrestrial ecosystems. Their reign was not accidental. It was built upon anatomical innovation, ecological adaptability, reproductive strategy, and continental scale opportunity. And even as the Cretaceous drew to a close, their dominance appeared unshakable. Until, in a single catastrophic moment, it ended. Yet their evolutionary story did not vanish entirely. It persists in every bird that takes flight today. The age of dinosaurs, though transformed, never fully disappeared. When the asteroid struck at the end of the Cretaceous period, it did not simply extinguish species, it dismantled a planetary system that had been structured around dinosaur dominance for nearly 200 million years. The extinction event, at the boundary between the Cretaceous and Paleogene periods was not merely the fall of large animals. It was the collapse of an ecological architecture that had defined terrestrial life since the Triassic. Approximately 66 million years ago, a bolide, roughly 10 to 12 kilometers in diameter, entered Earth's atmosphere at cosmic velocity. It struck the region that is now the Yucatan Peninsula, forming the Chicxulub crater. The energy released has been estimated at over 100 trillion tons of TNT equivalent. The immediate effects were catastrophic. Within minutes, seismic waves equivalent to earthquakes far exceeding magnitude 11 propagated across the globe. Coastal regions experienced megatsunamis hundreds of meters high. Molten ejecta was blasted into space, later raining back down through the atmosphere. As this debris re-entered, it generated intense infrared radiation. Forests ignited. Thermal pulses may have scorched continental surfaces thousands of kilometers from the impact site. But the longer-term consequences proved even more destructive. Dust, soot, and sulfate aerosols were injected high into the stratosphere. Sunlight was blocked. Global temperatures dropped rapidly. Photosynthesis halted or was drastically reduced for months to years. Without primary productivity, food webs collapsed from the base upward. Herbivorous dinosaurs, dependent on abundant plant matter, faced starvation. Carnivores, dependent on herbivores, followed. The extinction was selective but devastating. All non-avian dinosaurs disappeared. Yet extinction events are not solely about disappearance. They are about transformation. The Paleogene period began in a world stripped of its dominant terrestrial megafauna. Ecosystems were simplified. Large herbivorous niches were empty. Apex predator roles were vacant. Birds survived. These avian dinosaurs, small and adaptable, carried forward a lineage that had originated in the Jurassic among feathered theropods. Their survival reshaped the trajectory of life. In the earliest Paleocene, bird lineages diversified rapidly. Some expanded into large, flightless forms. Others refined flight strategies. Aquatic birds, wading birds, and arboreal species proliferated. Mammals, long overshadowed by dinosaurs, experienced explosive adaptive radiation. Throughout the Mesozoic, mammals had remained small, generally nocturnal, and ecologically constrained. Their survival through the extinction event allowed them to expand into newly vacant niches. Placental mammals diversified into herbivores, carnivores, and omnivores. Body sizes increased steadily during the Paleocene and Eocene epochs. Within 10 million years, mammals had produced species comparable in size to modern ungulates and predators. Yet the world they inherited was profoundly shaped by dinosaur legacy. Plant communities that had evolved under dinosaur herbivory continued adapting to new grazers. Angiosperms maintained dominance. Forest structures persisted, though modified. Avian dinosaurs filled aerial and certain terrestrial roles once occupied by small theropods. The extinction of non-avian dinosaurs was not due to inherent weakness. It was the result of rapid environmental disruption beyond adaptive capacity. For nearly 200 million years, dinosaurs had navigated climate shifts, continental drift, and volcanic upheaval. They had survived previous extinction events. They had diversified into polar regions and semi-aquatic habitats. They had evolved complex social behaviors and sophisticated sensory systems. Their downfall was sudden relative to geological timescales. The asteroid impact hypothesis is supported by multiple lines of evidence. A global iridium-rich layer marks the boundary between Cretaceous and Paleogene sediments. Shocked quartz grains indicate high-energy impact processes. The Chicxulub crater itself, buried beneath the Yucatan, provides direct confirmation. Volcanic activity from the Deccan Traps in India may have contributed additional climatic stress during this period. Some models suggest a combination of long-term volcanic emissions and the sudden impact created compounded environmental destabilization. Regardless of contributing factors, the outcome was definitive. Non-avian dinosaurs vanished, yet their evolutionary innovations did not disappear entirely. Birds retained hollow bones, air-sac respiratory systems, and feathers inherited from theropod ancestors. Many skeletal characteristics in modern birds directly trace back to Jurassic and Cretaceous dinosaurs. The wishbone, or furcula, present in birds today, existed in numerous theropods. Brooding behavior, observed in fossilized nests, parallels avian reproductive strategies. Egg structure and nesting colonies reflect continuity. Even aspects of behavior may persist. Territorial displays, vocal communication, and complex mating rituals seen in modern birds echo the display structures of crested hadrosaurs and horned ceratopsians. The post-extinction world evolved rapidly. During the Paleocene, climates remained warm. Tropical forests extended into higher latitudes. Mammals diversified into arboreal and terrestrial niches. Primates emerged. Early ungulates grazed on expanding plant communities. In marine environments, mosasaurs and plesiosaurs had disappeared alongside dinosaurs. Marine mammals would later evolve to fill apex roles, but this would take millions of years. The absence of large terrestrial reptiles fundamentally altered evolutionary pathways. Had the asteroid missed Earth, it is plausible that dinosaurs would have continued dominating terrestrial ecosystems. Mammals might have remained marginal. Primate evolution, including the eventual emergence of humans, may never have occurred. The dominance of mammals in the Cenozoic is therefore contingent upon the extinction of dinosaurs. Chapter 6 examines not only extinction, but transition. For 200 million years, dinosaurs were the default state of terrestrial megafauna. Their anatomical innovations shaped ecological dynamics across continents. They influenced plant evolution through selective feeding. They regulated prey populations. They structured food webs. Their extinction reset the biosphere. Yet evolution builds upon what came before. Avian dinosaurs remain among the most diverse and abundant vertebrates on Earth today. Over 10,000 bird species inhabit ecosystems ranging from Arctic tundra to tropical rainforest. In a literal evolutionary sense, dinosaurs never completely disappeared. They transformed. The fossil record preserves their skeletal architecture in stone, but living birds carry that architecture forward in motion and behavior. Modern paleontology has radically revised earlier conceptions of dinosaurs as slow, cold-blooded reptiles. Evidence accumulated over the past decades demonstrates active metabolism, complex behavior, and, in many cases, feathered integument. Isotopic analysis of bone chemistry suggests regulated internal temperatures. Growth rate studies indicate rapid juvenile development. Trackways reveal group movement. Nesting sites demonstrate parental care. The popular image of dinosaurs has shifted from lumbering reptiles to dynamic, adaptive organisms. The extinction event, while catastrophic, does not negate their evolutionary success. Dominance, lasting nearly 200 million years, exceeds that of any large terrestrial vertebrate clade before or since. Humans, by comparison, have existed as a species for roughly 300,000 years. The duration of dinosaur rule is almost beyond comprehension. Chapter 6 represents the closing arc of that rule. It is not a story of failure. It is a story of contingency. Evolution does not guarantee permanence. Dominance is temporary. Environmental stability is fragile. Dinosaurs thrived under the conditions of the Mesozoic world. When those conditions shifted abruptly beyond adaptive tolerance, extinction followed. Yet their legacy permeates the modern biosphere. Birds dominate skies and forests. Their respiratory systems, skeletal structures, and reproductive strategies are direct inheritances. Even aspects of ecosystem engineering trace back to dinosaur eras. The proliferation of flowering plants during the Cretaceous was influenced by herbivorous feeding pressures. Forest compositions today reflect deep evolutionary roots extending into dinosaur-dominated landscapes. The story of dinosaurs does not end at 66 million years ago. It branches. It continues in every avian lineage. It influences mammalian evolution indirectly. It shapes scientific inquiry and cultural imagination. The reign of dinosaurs was long, complex, and transformative. Their extinction was sudden but not absolute. Chapter 6 closes the age of non-avian giants, but it opens the era in which their descendants still fly above us. The age of dinosaurs, in one form or another, never fully ended. The end of the non-avian dinosaurs was not the end of their influence. Extinction removed their physical presence from terrestrial megafaunal roles, but it did not erase the structural framework they had imposed on the biosphere. When the Paleogene world emerged from the darkness of impact winter, it did so upon foundations built during nearly 200 million years of dinosaur rule. To understand the full magnitude of their reign, it is necessary to examine not only their rise and fall, but the systemic imprint they left on evolutionary pathways, planetary systems, and the trajectory of life that followed. The Mesozoic era, spanning roughly 252 to 66 million years ago, was fundamentally shaped by dinosaur-driven terrestrial ecosystems. From early Triassic archosaurs navigating post-extinction landscapes to Cretaceous titans structuring complex floodplain communities, dinosaurs were not merely inhabitants of environments. They were ecosystem engineers on a continental scale. Large sauropods altered vegetation structure through high browsing. Their feeding created canopy gaps and maintained open woodland mosaics. The mechanical stress of their movement compacted soils and influenced plant regeneration cycles. Nutrient redistribution through excretion likely enhanced localized fertility, shaping plant community distribution. Ornithischian herbivores, such as hadrosaurs and ceratopsians, processed vast quantities of vegetation. Their specialized dentition and jaw mechanics allowed exploitation of angiosperm-dominated ecosystems during the Cretaceous. Selective feeding pressures likely influenced plant defensive adaptations, including chemical deterrence and structural modifications. Predatory theropods regulated herbivore populations, preventing unchecked grazing pressure. Apex predators function as stabilizing agents within ecosystems. The long-term persistence of theropod lineages suggests sustained ecological equilibrium across vast timescales. This stability was not static. It evolved gradually, alongside tectonic and climatic change. Continental drift during the Mesozoic reshaped global geography. The breakup of Panjia initiated isolation events that produced endemic faunas as continents separated, ocean circulation patterns shifted, climate gradients developed. Evolutionary experimentation accelerated within isolated regions. South America's prolonged separation fostered distinct theropod and sauropod radiations. Asia's partial isolation facilitated diversification of feathered theropods. North America's western interior seaway created evolutionary divergence between eastern and western faunas. Over tens of millions of years, this mosaic of isolated ecosystems produced extraordinary morphological innovation. Feathers, initially evolved for insulation or display, became aerodynamic surfaces. Respiratory air sac systems allowed efficient oxygen exchange, supporting both gigantism and flight. Skeletal pneumatization reduced mass without sacrificing strength. Reproductive strategies emphasizing egg-laying enabled rapid population recovery following local disturbances. These anatomical systems were not independent innovations. They were interconnected evolutionary solutions to ecological challenges. The survival of birds through the end Cretaceous extinction demonstrates the robustness of certain dinosaurian adaptations. Small body size, rapid growth, flexible diet, and advanced respiratory efficiency likely conferred resilience in post-impact conditions. In the early Paleocene, birds rapidly diversified into ecological niches previously occupied by small theropods and some herbivores. Large, flightless birds evolved in certain regions, assuming terrestrial predator roles. Aquatic birds exploited coastal and freshwater environments. Mammals, liberated from Mesozoic constraints, underwent adaptive radiation of unprecedented scale. Yet, even mammalian evolution was indirectly shaped by dinosaur legacy. Flowering plants that had proliferated during the Cretaceous continued dominating terrestrial flora. Mammalian herbivores evolved dentition suited to angiosperm consumption. Forest structures, initially molded under dinosaur herbivory, influenced mammalian locomotion strategies, including arboreal adaptations in early primates. The extinction event that ended non-avian dinosaurs was catastrophic, but it was not total annihilation of Mesozoic ecological systems. Many plant groups persisted. Insect lineages survived. Freshwater ecosystems retained structural continuity. The fossil record across the Cretaceous-Paleogene boundary reveals selective survival patterns. Organisms capable of burrowing, sheltering in water, or surviving on detrital food webs exhibited higher survival rates. Small size conferred advantage in conditions of reduced primary productivity. Large body size, once a hallmark of dinosaur success, became a liability in a resource-starved world. For nearly 200 million years, however, large body size had been an effective strategy. Gigantism reduces predation risk, enhances digestive efficiency, and stabilizes internal temperature. Sauropods exemplified this principle. Their size deterred most predators once maturity was reached. Tyrannosaurids, though massive, required stable prey populations. The collapse of herbivore communities following impact winter would have been fatal to large carnivores. Extinction events highlight the contingent nature of dominance. Dinosaurs thrived under Mesozoic greenhouse conditions. Their physiological systems were optimized for those environments. When rapid global cooling followed impact, adaptive capacity was overwhelmed. Yet the broader evolutionary lesson is not fragility alone, it is persistence across immense spans of time. Dinosaurs survived multiple earlier crises, including the end Triassic extinction and various mid-Mesozoic environmental fluctuations. Their anatomical versatility allowed colonization of polar regions, semi-aquatic habitats, and diverse forest ecosystems. Evidence from Antarctica reveals dinosaurs adapted to seasonal darkness. Bone histology suggests continued growth during winter months, implying metabolic regulation rather than reptilian dormancy. Spinosaurus demonstrates exploration of aquatic niches. Microraptor and other small theropods show arboreal adaptations and gliding capabilities. Diversification was not linear, it was multidirectional. By the late Cretaceous, dinosaurs occupied nearly every terrestrial niche available to large vertebrates. Herbivores ranged from heavily armored ankylosaurs to agile bipedal ornithomimids. Predators ranged from small feathered insectivores to colossal tyrannosaurs. This ecological saturation underscores the magnitude of their evolutionary success. The Paleogene world, though transformed, retained structural echoes of Mesozoic systems. Avian dinosaurs diversified across continents. Their respiratory systems, skeletal lightness, and reproductive strategies proved adaptable to new climatic regimes. Mammals expanded into niches once dominated by dinosaurs, but they did so gradually. The early Paleocene lacked megafauna comparable in size to late Cretaceous giants. It would take millions of years for mammals to produce species approaching sauropod scale in mass, and even then, none would rival the largest dinosaurs. Modern ecosystems remain shaped by patterns established during dinosaur rule. Predator-prey dynamics, herbivore-driven vegetation modification, and migratory behaviors have deep evolutionary roots. Even the carbon cycle during the Mesozoic was influenced by dinosaur-dominated plant communities. Extensive forests and high atmospheric carbon dioxide levels characterized much of the era. Interactions between herbivores and vegetation influenced carbon sequestration patterns. Chapter 7 represents reflection. It examines the legacy of nearly 200 million years of dominance and the enduring imprint left on Earth's systems. Dinosaurs were not evolutionary accidents. They were adaptive radiations that capitalized on ecological opportunity following mass extinction. Their success was reinforced by anatomical innovation, reproductive strategy, and environmental alignment. Their extinction, though abrupt in geological terms, was the result of extraordinary external forcing rather than gradual competitive decline. Had the Chicxulub asteroid missed Earth, it is plausible that dinosaurs would have continued dominating terrestrial ecosystems well into the Cenozoic. Mammals might have remained minor components. Primate evolution might have followed an entirely different trajectory, or perhaps never achieved ecological prominence. Human existence is therefore indirectly contingent upon dinosaur extinction. This perspective reframes the narrative. The fall of dinosaurs was not simply the end of giants, it was the opening of evolutionary space for mammals, including eventually humans. Yet humans are recent arrivals. Dinosaurs ruled Earth's continents for a duration nearly 600 times longer than humans have existed as a species. Their reign encompassed tectonic reconfiguration of continents, evolution of flowering plants, diversification of insects, and multiple climatic oscillations. Few lineages in Earth's history demonstrate comparable longevity at ecological apex. Modern paleontology continues uncovering new species, refining phylogenetic relationships, and reconstructing behaviors once considered unknowable. Advanced imaging technologies reveal internal bone structures. Isotopic analysis reconstructs paleodiet. Biomechanical modeling simulates locomotion and bite forces. With each discovery, the image of dinosaurs becomes more dynamic and complex. No longer portrayed as primitive reptiles, they are understood as highly adapted archosaurs exhibiting diverse behaviors, metabolic strategies, and ecological interactions. The age of dinosaurs was not a static, prehistoric backdrop. It was a prolonged evolutionary experiment in dominance. Chapter 7 closes with the recognition that extinction does not erase influence. Avian dinosaurs persist. Their evolutionary innovations continue thriving. Ecosystems shaped under Mesozoic conditions laid groundwork for Cenozoic diversification. The reign of dinosaurs was vast in duration and transformative in scope. Their story is not solely about extinction. It is about persistence across deep time, about anatomical innovation responding to planetary change, and about the contingency that defines evolutionary history. For nearly 200 million years, dinosaurs ruled the land. Their legacy still surrounds us, not as fossilized relics alone, but as living descendants and ecological structures that trace back to a world once governed by giants. Dinosaurs navigated internal processes masterfully. Their adaptive radiation demonstrates evolutionary creativity on a planetary scale. External forces, however, intervened. The asteroid impact was not selective in a traditional evolutionary sense. It did not reward superior adaptation within existing ecosystems. It reshaped the environment so drastically that previously advantageous traits became liabilities. Large body size required stable food webs. When photosynthesis collapsed, stability vanished. Small size, dietary flexibility, and sheltering behaviors favored survival. Birds and mammals inherited the future. Yet the dinosaur legacy remains instructive. It demonstrates that ecosystems can sustain dominant lineages for immense spans of time. It illustrates how anatomical innovation can open ecological opportunity. It reveals how continental drift and climate shape evolutionary trajectories. And it reminds us that dominance is always provisional. Humans today exert planetary scale influence, yet our species has existed for a fraction of the time dinosaurs ruled. Their story encourages humility. It also encourages scientific curiosity. Modern paleontology continues refining our understanding of dinosaur physiology, coloration, behavior, and ecology. Advanced imaging technologies reveal soft tissue impressions and melanosome structures, allowing reconstruction of feather coloration in certain species. Isotopic studies infer migratory patterns and dietary specialization. Each new discovery expands our comprehension of a world long vanished. But that world is not entirely inaccessible. It is recorded in sedimentary rock layers across every continent. It is preserved in fossilized trackways etched into ancient mud. It is encoded in the anatomy of birds that soar above us. Chapter 8 concludes not with extinction, but with continuity. The age of dinosaurs was vast, dynamic, and transformative. It shaped the biosphere in ways still unfolding today. For nearly 200 million years, dinosaurs were the defining terrestrial vertebrates of Earth. Their rise from small Triassic archosaurs to Cretaceous giants represents one of the most remarkable evolutionary narratives in planetary history. Their fall, triggered by cosmic chance, opened pathways for new lineages, but their influence persists. In every feather, in every avian lung drawing unidirectional breath, in every fossil unearthed from Jurassic stone, the echo of their reign remains. The age of dinosaurs was not a brief prehistoric chapter. It was an era of planetary-scale dominance. And though the giants are gone, their legacy endures in stone, in science, and in the living descendants that still inherit the sky.